So we're going to talk today about the basics of building science, and again, it would be fun if we could spend more time on this, but we cover it briefly to kind of tie it into the energy code. You'll see why the stuff is in the energy code.
Yeah, I mean, really, what we're going to talk about is the movement of heat, air, and moisture within buildings. We're going to try and give everybody sort of either a refresher or kind of a basic amount of information about building science. And then as we go throughout the day, you'll see how that sort of relates to the energy code. Because what is the energy code trying to do? Well, in some ways, manage the flow of heat, air, and moisture in buildings. So,
okay, Burke?
All right, this is a concept that we refer to as the building as a system. We're going to talk about the envelope, and that's the first thing we're going to look at in the energy code today. And the energy code does say that the envelope, thermal envelope, is made up of two parts. It's made up of insulation and an air barrier. They need to be continuous, and they need to be in substantial contact. Really, the purpose of the building's thermal envelope is to define what is conditioned space and what is unconditioned space. We're looking at a picture here, kind of a house, but you can see there are, within the shell of the structure, some spaces that have been defined as conditioned and some spaces that have been defined as unconditioned. So there's flexibility in how you define the building's thermal envelope, but wherever you draw that boundary, it's got to have an air barrier and it's got to have complete insulation coverage. Other than that, we're going to talk about once you've defined the envelope and once you've made an envelope that's relatively tight, how do you come up with the proper sizing for the HVAC equipment that's in it, and then how do you provide ventilation to that space? Because if we make the building envelope tight to control our energy expense, we also want to make sure that we're bringing in some ventilation air.
And then if you were here, we talked about this on Monday for the residential training. Which of those three kind of main bullets is not a requirement in a house? Which one do you actually not have to do in a house? The intentional ventilation. What about, do you have to do ventilation in a commercial building? Yes, you do. Yes, you do. So commercial buildings, you could argue, are a little further along in that they're requiring us to do all three of those things. We have to do all three of those. And it's a combination of the energy code and mechanical code and so on. But it's making us, in essence, do what we should be doing. So the last one on here, deal with moisture, we always throw that in there because it's kind of indirectly related to energy, but obviously it has a significant impact on durability. All right, Burke. Oh, look, this one has, everybody see that?
I like it when things work automatically.
I want to see it again.
All right. So as this graphic is demonstrating, the flow of heat is always from hot to cold. Basically, I say heat wants to flow downhill. Path of least resistance, and it moves in three forms: conduction, convection, and radiation. And we're going to take a look at each one of those and talk a little bit more. But conduction is basically heat flow through a solid. Convection is heat flow through air. And radiation is surface to surface with nothing basically completing the pathway in between. Anybody want to guess what we're looking at here? And don't say a photograph. I've heard that one before. All right. It's an infrared image, and on the left we're looking at a picture of the building assembly, and on the right we're looking at a thermal image. And basically we can see it's cold outside, they're heating inside. We can see the dark areas where we've got basically some pretty good insulation, and we can see some bright red areas. And we've got a section of the wall right here that's almost the same color as the window transom above the door. So any idea what's probably going on in that assembly? I heard no insulation, right? So we're basically looking, and there is very little resistance to conductivity in this part of the wall. And of course, as I said, heat's lazy. It wants to take the path of least resistance. So it's basically flowing through the least resistant part of the wall. There's really no better insulation going on here than we have up in the transom window. So any idea why this might have happened? That's it. Somebody right off the bat. People are usually like window, door, I don't know. We think probably a shower stall assembly here went in at framing insulation, didn't get put in behind it, and you basically end up with a big thermal breach. On top of that, it's going to be a comfort issue. This is a residential home. That bathroom is always going to be cold. It's not going to be a pleasant place to take a shower. So got a comfort issue there as well as basically an insulation issue.
And this is one of the reasons why I think an insulation inspection is so important to catch it before drywall, to go and actually see, did they insulate behind the tub? Because the tub, of course, often gets set, before insulation shows up. So it needs to be done, and conscientious builders are paying attention to it. But you have to what is it? You have to inspect to get what you expect. I think is that what they say, or something like that. So that was conduction. Of course, to slow it down, we use insulation, but we don't want to use insulation to slow down airflow, right? Because that's what we're seeing in this picture. And the movement of hot air or cold air in or out of a space is convective heat transfer. And to stop that, we need real air sealing materials. So the picture here, again, is showing air leaking under a wall bottom plate, it looks like, and that was, again, a cold sign. And the dirty insulation is telling us that the insulation was acting like what? Yeah, a big filter, right? So the filter effect of the insulation is evident. That's a visual clue that no air sealing had been done, and that looks like a plumbing chase or something, or some sort of plumbing penetration. So those are the kind of things that you're going to see the commercial code very much emphasizes air sealing, as does the residential code. So fiberglass insulation does not stop airflow. Everybody buy into that? Anybody, I think we're getting better understanding of that. We used to see a lot, people would do things like, there's a hole around the bathtub, I'll just shove a fiberglass bat in, or someone would chink insulation around a window rough opening, and that's not an air barrier. That's not an approved air sealing means. So I think we're making good progress on that. Okay.
The third type of heat transfer we mentioned is radiation, surface to surface, basically not happening through conduction or convection. Best example we can give of this is, of course, the sun. So the sun is a big source of radiant heat. I think we're demonstrating that with this graphic. Big sun, lots of heat, little Earth. It's kind of an interesting concept to think about the transfer of heat from one surface to another surface without it being carried by something. Where are we really dealing with radiant heat in buildings?
Where does radiation sort of dominate in buildings? Windows is one of them.
And the attic. Exactly right,
and
the roof.
Yeah, skylights for sure. Skylights even more than windows because of the angle and the tilt, but also the roofs themselves. So those are the kind of places where those things really dominate. So if you were here Monday, you saw this, a little exercise in heat transfer. How does the heat, here's a kind of this could be a commercial building, but it's sort of a residential style attic assembly. Mm-hmm. Where the energy is traveling from the sun to the shingles on the roof. What type of heat transfer is that? It's going through space, right? There's no fluid in there, and there's nothing solid, so it has to be radiation, right? Okay. All right. What next, Burke? What's going on?
So 2 to 3 here. Basically, we've got the sun shining down, hitting our solar collectors here, and then transferring through into the inside of the attic assembly. So that's an example of conduction. If you know the answer, just yell it out.
Are you allowed to answer out loud?
You can. You are allowed to answer out loud. So exactly, the heat is basically transferred from exterior to interior via conduction. So that's what's happening in 2 to 3.
And before we go too far, again, the roofing material is a big player in how much solar energy that whole assembly is going to absorb, right? And we make a big deal out of this in the other training, but how, I think it's pretty obvious. What are the factors why do shingles absorb, so much of the sun's energy?
Magic.
What about a typical roof shingle is making it absorb so much energy? It's
black.
It's a dark color typically, right, for aesthetics, so it doesn't stain, and that's very absorptive. What about the surface of a shingle? Is it real smooth? No, it's a textured, granular kind of approach. That's very good. And then of course, it's leaning at the sun. So those three things mean that it's an incredibly good, we call it a solar collector, a solar absorber. And we're going to see in particular in commercial buildings, there's actually within one of the codes, there's an option that allows you to take credit for doing something smart on a roof. And not having such an absorptive roof material. Okay, so.
Good teaser.
Yes.
All right. So basically we've talked about the energy getting from the sun down to the roof via radiation, and the transfer from 2 to 3 here, from outside to inside via conduction. So what do you think's going on here from 3 to 4, the backside of this attic assembly down to the mechanical systems inside? What type of heat transfer is occurring there? Yep, radiation. I heard 2 correct answers, and no one wanted to say it real loud. Radiation. So again, here the heat is then basically radiating off the backside of this attic assembly and down into the other surfaces within the attic. So again, we have that radiant heat transfer occurring. Then that leaves us with 5, 6, and 7, which is what? Convection. Very good. We're basically trying to cool down the attic convectively by bringing in some outside air and then venting it through there, basically sucking in colder air, expelling warmer air, using some of the stack effect to do that. It's an example of convection.
And I've got a couple samples. We talked about how products like this that can go in the roof decking, as opposed to this surface, in a standard roof, by having a low emitting surface, a radiant barrier. What's the advantage of this? What does this do for us? No, it kind of. It's sort of very confusing because we always want to think it reflects the heat back. It kind of, really what it is it doesn't emit the heat by radiation. It slows the heat gain down in the assembly, I think is a better way to describe it. But it really will keep the attic, cooler. Anybody been in a building that has this installed in it before? Did it work? Do you think?
Yeah, it's still hot, but it works.
Yeah. Yeah. I mean, well, it'll probably knock about 20 degrees off the attic air temperature. Maybe a little more. But yeah, I think it actually does work. And the idea about this product, it's called a low emitting surface, because while it does get hot, just like if it looks like this, it gets very hot. It doesn't give off its heat very easily. So it's a low emitting surface.
You also have some problems with heat gain on the bottom of your shingles too. They require a lot of times a ventilation layer.
Actually, today, pretty much every shingle manufacturer is okay with you using this. It won't mess up your warranty.
Coded, that's all.
Pardon it?
Just the building coded.
The building code isn't? No. This is okay. You can do this. You can still. I mean, you still vent under it.
Yeah.
But you can still vent under it. That's okay. But the whole thing about this surface is that it just doesn't give away its heat, and it basically slows down the overall entry of heat into the attic assembly. It doesn't really have much effect on the shingle life because the shingles are really being cooked by something else, right? Not the decking. What's cooking the shingles? The sun, right? So in terms of commercial buildings, if you're going to do a vented assembly like you see here, then I think this is a very good product, especially the further south you go. This is a really good idea. I don't know that it will gain you any credit per se in terms of the energy code. It would actually potentially downsize your equipment, and it will offer some energy savings. But it's not the same as if you had, in essence, a shiny roof out here. That is given some credit in the code. One of the things I did want to emphasize, though, is we could rethink our whole attic assembly. Instead of a flat ceiling with insulation, what's an option we could do instead? Yeah, we could go along, we could change our envelope. And I want to emphasize that I think for commercial buildings, this is what we should do a lot. I think venting roofs is kind of a little bit of sort of what we think is a good idea because someone told us it was. Residentially, a lot of times we have a flat ceiling. Basically, if you have this assembly, yeah, you probably should vent above it. But when you vent a roof or vent anything and you live in Georgia, what are you actually letting in when you vent? You're letting a lot of humidity in, right? Yeah, a lot of moisture. So that's a concern. I think commercial buildings, we really would be better served generally to not vent and to just run insulation along the roof line. And I think that I have seen through my course, and you've done a lot of energy assessments on existing buildings, I have seen many problems in commercial buildings where people don't understand what they're venting or why they're venting, and all they end up doing is letting in moisture and essentially bypassing their insulation. And it does not save energy at all. It wastes energy, and it causes, amongst other things, you ever seen water spots on a drop ceiling in a commercial building? Right? If we look hard enough, I know we can find some. Right? There's always some somewhere, right? The room we were in the other day, they had painted it. It was they were painting over the water spots periodically. You could tell. So that's something to consider. That really venting in a commercial building on a roof, unless it just really looks like a house like this, I would typically say you're much better off trying to put your insulation and make it continuous. And it seems like more times than not, I've seen commercial buildings where someone thought they needed to vent it, and they stuck vents in a soffit, and that was all they did. And basically, they just essentially let all kinds of moisture in.
But you still have both the requirement of the building code for venting attic spaces as well as shingle I came to one of these seminars several years ago.
Yeah.
And preached the same thing. You still have shingle manufacturers though saying if you don't ventilate that attic, the warranty on our shingle.
But not all shingle manufacturers are like that. So
I can pick one, I guess.
yeah. I mean, I'm offering you this as advice. This is not a code mandate.
Well, I think it's good advice. My question is why don't we work with the code officials to get that changed in the state?
I agree. It's. I mean, you have to appreciate too that the construction industry is an interesting ship. That you get companies that have a very vested interest in the ship continuing on its current path. Meaning, my company makes a whole lot of ventilation products, and in some climates they may be more good than bad. But you could argue in the South that really the value they bring to commercial buildings. And we're going to see this as we go deeper, but lots and lots of times people put vents in, they don't know why, and they end up letting in moisture, and it causes energy waste, moisture problems, and basically decay of the building, durability issues. So I hear what you're saying, and you're exactly right. There are companies that still say you got a vent under their shingle. They'll do anything to, they don't want to do anything to get it, or they will happily get out of the warranty on any situation. But there are companies that also understand the physics that what you do under the decking, under the shingles, has very little effect on the actual life of the shingle. That's being cooked by the sun. And we have a whole section on roofs. So, but yeah, again, I'll reemphasize: if it looks like a house, it's probably more good than bad to do the standard venting. By the way, do not use a power attic vent fan. Don't use a fan. Just all passive venting. Anybody remember from the residential training, why do we not want to put a fan up here and depressurize the attic? Yeah, because that's exactly right. It'll cool the attic for sure, but it'll actually pull air conditioned air from down in here up into the attic, and it's because it's hard to get a perfect air seal across here. So don't use a fan if you're going to vent. But in general, on commercial buildings, I really am going to recommend that you just try to change the envelope so that it's not doing that. That's a general statement. Joe?
Yeah, well, the amendments actually made it easier for the code officials to do that under their definition of space.
Correct.
They gave you this new definition,
Correct.
which I think really now everybody can read on the same page.
That is true. That is true. Any other thoughts or comments or questions on this? Okay. Ready?
I think we're ready.
Okay.
All right.
Uh-oh.
So
Oh, look, more innovation. Whoa. Wait, do that again. Oh, look.
basically,
Whoa.
air movement. Air is always going to move from an area of high pressure to an area of low pressure. Again, downhill, air is lazy. It wants to go from where there's a higher concentration of pressure to lower concentration of pressure. When we look at air movement, basically we talk about air movement in and out of structures. There's bad things about air leaking out of your building. There's bad things about air leaking into your building. So we really want to look at the energy code, focus on air sealing, and try and control the flow of air in and out of the building. Basically, so that we're reducing the uncontrolled infiltration into the building and then providing intentional ventilation so that the people inside the building can breathe. Let's see what the next slide is.
And then the last bullet, I think you should mention that as well.
Yeah, so basically whenever a volume of air moves in or out of a building, it has to be replaced. So if 50 CFM of air is expelled out of a building, 50 CFM of air wants to come into the building. So basically the building has the intention to try and balance itself from a pressure standpoint. What this basically means is if we've got continuous exhaust in this climate, if we've got big fans that are running in the building exhausting air out, we've got to have a plan for balancing that, or else we're just going to have a negatively pressurized building that will Suck. Okay, very good.
Suck. Okay, I didn't say suck
Nobody
at the
got
right
that.
time. I'm sorry.
All right, so
Suck. Sorry, what was that? One thing, too, you kind of notice that term infiltration, it sort of implies air leaking in. That's kind of a cold climate mindset. You know, it's people in a cold climate that I don't want infiltration because that means cold air is leaking in. But appreciate that our climate, it's conditioned air leaking out is the same thing. So infiltration, it's really better to call it air leakage. And the same amount that leaks in is equal to what leaks out. And I think that's always worth remembering. So the things that cause it to go, look, watch, more graphic. Are you excited, Joe? Did you see that? All right. Okay, I know, look at that, the high pressure. In general, would we rather have our building look like this, where the building is positive with reference to the outside, or would we rather have our building look like this, where the building is negative with reference to the outside? What's our preference here in the South? Do our buildings want to be positive or negative? Why is that? That's correct. Why is that? Why would we rather have our buildings positively pressurized?
humidity.
I think a lot has to do with moisture and basically keeping the humidity at bay, so to speak. So in commercial buildings in particular, this is something we want to strive for. And now there are places within the commercial buildings we want to pull air out, right? We want to exhaust air from toilets and things like that, janitor closets. But in general, we would rather put back more than we pull out. So our building is slightly positive in this climate, or at least neutral. We don't want our building to suck for a long time, right? To be under negative pressure, because that really could cause moisture problems. That causes air to come in from where we don't want it. So I'd say in general, think positive pressure on buildings. Think positive. All right, what are the other things?
Well, basically what we're looking at here is in order for infiltration to occur or air leakage to occur, we need two things to exist: a pressure difference and a hole or a pathway for the air to travel through. So if you eliminate one of these two things, you're basically going to manage the air leakage in a building. Of course, the Energy Code is now requiring us to do mandatory air sealing, basically as a way to try and reduce the number of holes that are in this building's thermal envelope.
So the driving forces?
I just mentioned a few minutes ago mechanical fans. Obviously, that's one of the driving forces in a commercial building. We also have something called, this is wind. I was going to go to stack effect. We also have wind. Obviously, the larger a building is, the bigger the shell of the building is, the more wind is an effect on it. What we're looking at here is a picture that basically is demonstrating how wind can create a high-pressure zone on one of the building facades while creating a low-pressure zone on the other. So basically, you can have one facade which has the wind pushing against it, creating a high-pressure zone. On the leeward side over here, you've got a negative pressure zone that's created. So wind is a natural occurrence, and as the building gets larger, wind has a greater effect on basically the pressure difference from outside to inside in that building. So this is what I was alluding to a minute ago, stack effect. Stack effect is basically pressure differences that are driven by the buoyancy of air. The warm air wants to rise in these structures. I'll probably talk about this on Tuesday. Within a residential structure, stack effect exists, but it's probably not going to create really dramatic pressure differences. The taller a building gets and the larger the sort of interior open spaces are, the bigger effect you're going to have from stack effect. So when you have, let's say, a 10-story open atrium hotel, you're going to have a very large amount of stack effect in that space because you've got a big open chamber that has a very dramatic height difference. And so you've got basically warm air pushing out at the top. That's creating a positive pressure zone, and that's creating also a low pressure zone at the bottom. So basically you have air wanting to push out at the top of the structure. You're trying to make up for that in the building with air being sucked in down at the bottom of the structure. The taller the building gets, the bigger stack effect is the bigger role stack effect is going to play in pressure differences within the building.
And you're going to see this showing up in the Energy Code because the Energy Code is starting to push harder and harder for kind of an airlock down here on the entryway, basically vestibules. Vestibules become bigger and bigger, it seems, as the Commercial Energy Code progresses. And as you go to taller buildings, it becomes more of an impact.
And we're going to look later today, the two different code pathways kind of have two different recipes for what you need to do with vestibules, and we're going to look at that this afternoon.
Okay. So it is kind of interesting that if you had a hole down here at the bottom and a hole down up here at the top and one right here in the middle, the air would be leaking in at the bottom. It would be leaking out at the top. What if you had a hole right here in the middle? What would happen at that spot?
Nothing.
No air leakage, right? And this is a picture that we showed this in the residential one too. This is a multifamily building that you can actually see. It looks like they were doing some construction and essentially covered this, probably a stairwell or something here on the corner, and it's a giant. Essentially, it's like a hot air balloon, kind of a tarp, if you will, almost like a blower door tarp. And what is happening here at the top? What's the tarp doing? It's bulging out. It's blowing. The balloon is blowing out, and then what's happening down here at the bottom? Sucking in, and then in the middle, you got the neutral pressure plane. So it's kind of cool. It's really a neat picture that really shows what's happening in a real live building, and that's all due to the stack. That's not the wind, and it's not a fan. That's the stack effect. So like Burke said, it's a function of the height of the building. It's also a function of the temperature between the inside and the outside. So you tend to see more stack effect in the wintertime. It's colder, there's a bigger temperature difference. And then the last section is mechanical fans.
We kind of alluded to this. Obviously, the bigger the building gets, the bigger the mechanical systems get, the bigger the fans are. And whenever we're moving air around a building, you have basically the opportunity to create positive and negative pressure differences within the building itself. And also going back to the idea of whenever we exhaust air out of a building, the same amount of air wants to come into the building. So the bigger the mechanical fans get, the more you really need to plan to basically have balanced pressurization. The same amount of air being made up is being exhausted out of the building.
All right, so to kind of recap, which would you say is sort of more impacted by the driving forces? Let me try to set up a question here. You got a one-story house, or you've got a 10-story, let's just take a big 10-story building with an elevator shaft and all this, and maybe a big atrium in it. So which one is probably going to be more susceptible to the wind? The big building or the small house? The big building. Which one is going to be more susceptible to the stack effect? The big building or the small house? And which one, it probably has bigger fans creating bigger pressure differences? The big building. So we're kind of trying to make this point here that commercial buildings, air sealing in commercial buildings is you could argue even more crucial than in homes. Not that it's not heavily emphasized in homes, and Brian went through a class that requires us to test the tightness of a home. But what we're really saying is that the tightness of a commercial building, because the driving forces arguably are more strong in a commercial building, it's even more crucial. So the energy impact is pretty significant. If you're trying to maintain a building under, say, a positive pressure, it's much easier to maintain a tight building under positive pressure than it is a leaky building. Does that make sense? It kind of, try to blow up a garbage bag that has a whole bunch of holes poked in it. It's pretty hard to do if there's a whole bunch of holes poked in it. It's pretty easy to do if it's pretty tight. Do we need to demonstrate that?
No.
I don't think we go dig in the garbage. So that's kind of, I think, our big take on air sealing. So a very crucial part of the energy code is air sealing.
And then finally, wrapping up with moisture here. Obviously, moisture is always going to flow from wet to dry. And we basically break moisture into two sort of categories here. We've got liquid and vapor. So over on the liquid side, we've got bulk moisture. These are plumbing leaks, drainage issues. If you've got one of these issues, it's pretty obvious. And we know that it's really important to deal with bulk moisture in buildings. We've also got capillarity, which is basically driven by the porousness of building materials, the wicking effect. Most masonry, wood, a lot of building materials are porous, and they will wick water. Again, mostly related to when you've got bulk moisture issues on site, and then wicking can occur through the building materials. Over on the vapor side, we've got diffusion and infiltration, and these are basically looking at moisture that's in the air and how it could possibly get into buildings. Diffusion is basically air movement at the molecular level. It takes a long time, and it's about the air basically diffusing through building assemblies. Infiltration, on the other hand, happens really rapidly, very quickly, and we're actually able to bring large volumes of moisture unwantedly into a building because of infiltration. So what we're looking at here is basically a demonstration of the amount of moisture that can move into a building via diffusion or via air leakage. So over on the left, we've got a picture of an 8x4, or a graphic of an 8x4 sheet of gypsum board. This is over a heating season. We're looking at roughly 70 degrees interior, 40% relative humidity, and the amount of diffusion that is going to occur through that piece of wall board. So basically, how much moisture is going to work its way through at the molecular level, and we're looking at about a third a quart of water over a heating season. Does that seem like a lot of moisture for your HVAC system to have to take out of the air?
Well, no, it's going out of your building in this case.
Going
But
out of your building.
it's
Okay, so
relatively small in terms of the entire, 5 months heating season, whatever it is. That's not a lot of water vapor diffusing across just an unpainted piece of gypboard. And of course, when you paint it, it'll be even less.
So then over on the right, we've basically got the same conditions and the same sheet of board, but we've put a 1-inch square hole in it, and we're looking at 100 times the moisture content. So basically a lot more moisture which is able to move through this 1-inch hole than is able to diffuse through the board. So what does this tell us? Which is a bigger issue, diffusion or air leakage? Air leakage.
Yeah.
100 times bigger deal. So air leakage is a bigger issue in managing how water vapor is moving through buildings than diffusion is. So what is...
I was just going to say, of course, this is a study done in the wintertime, basically looking at, it's cold and dry outside, and water vapor is trying to go, sort of from more to less. But really, in our climate, the water vapor is where? It's all outside, or a lot of the year, right? It's outside, and it's trying to come in, and that's another reason why we can help, keep our buildings positively pressurized, keep it at bay, but also it's really about air sealing. I guess that's the big takeaway. Do I need to worry about a vapor retarder really in a wall assembly here in Georgia? Do I need to worry about an air barrier in a wall assembly? Yeah, big time. That's probably the takeaway I hope you get from that. Vapor retarders are something that I think, they make sense in Canada, but they came way too far south. And y'all were taught wrong. I'm going to just say it. Whatever you were taught, how long ago? 150 years ago when you were in school, that was wrong. I mean, and we just took it way too far south. There is nothing in the Commercial Energy Code that requires you to use a vapor retarder. The one place that we should use a vapor retarder is down. In other words, underneath the slab, or on the floor of a crawl space or a basement slab. That's where we do want plastic. But in the walls, in the ceiling, as a general statement, we do not need that. In fact, if we put plastic on the inside of a wall and we live in a humid climate, why could that be a bad thing? You got it. We could be trapping the moisture from being able to, in essence, to dry through if it needs to dry, if it's in the wall and it's really humid outside and it's cooler and drier inside because we're air conditioning. If we trap it from being able to get there, it condenses on plastic. Then we actually could rot some walls down, and that has happened. All right, let's do a little survey. This is our Gulf Coast motel survey. All right, so raise your hand if you've been in a motel or hotel on the Gulf Coast and you walked in and it smelled like mold. Okay, and what do they put on the inside of a lot of commercial buildings, particularly motel and hotel? What do they put on the inside of the wall? How do they finish the wall out?
Vinyl wallpaper.
Vinyl wallpaper, right? Which is basically what? A vapor barrier, right? Now, they're supposedly, if they're smart, they run it. There's a machine that you can poke a bunch of holes in it, little micro perforations. But a lot of people don't do that. And as a result, they end up putting a vapor barrier on the wrong side of the wall in a humid climate, and they trap moisture, and that is bad. That is a problem. So really, can you think of an example in a commercial building where you might actually want to put a vapor retarder in the wall or ceiling? Think about what might be going on inside a building that might, in essence, create a lot of humidity. What sort of indoor? Can you think of something?
Natatorium.
Ah, there you go. Swimming pool, natatorium, same thing, right? So an indoor pool, that might be one exception to the general statement that I just made. But this is where, to me, you hire someone that understands moisture and understands mechanical, what are we trying to do here, and has that knowledge. That might be a case where, of course, air sealing is crucial in that natatorium, and the airlock and everything is important. But, a pool is a big humidifier, right? So having that room might need a vapor retarder on the inside. Otherwise, in a standard wall assembly, I would say don't go that way. Here's a question. What if I just said, well, I'm going to put a vapor retarder on the inside and the outside of the wall? Is that a good thing or a bad thing? Does anybody remember where we did that on some buildings? We put more houses, and it was just bad directions for us. We put plastic on the inside, and what sort of coating did we put on the outside that ended up being a vapor retarder? Does anybody know what I'm talking about? Yeah, the EFIS system, right? And it was an EFIS system that did not have a drainage plane. That EFIS can work really well. Don't get me, I like synthetic stucco as a finish. It's on our building. I like it. As a cladding, it can work pretty well. But the synthetic stucco needs to have a drainage plane behind it, or at the very least, needs to be installed on a mass wall. Mass walls have a lot of moisture sort of cushion built into them. Heavy walls, concrete, they can take a hit of moisture and probably not rot down, right? But a steel frame assembly, the only thing in that steel frame assembly that can handle any even a remote amount of moisture is probably the gypboard, and not much. Okay, so in that assembly, we've got to have a drainage plane behind the synthetic stucco. If you put a light gauge wall and you put plastic on the one side and a non-drainage plane stucco on the other side, what have you created in here? What is
moisture trap?
A what now?
A moisture trap.
Right? Or a terrarium. That's another way. Right? A failed double pane window, right? Something like that, right? So if moisture gets in and it can't get out, that's a problem. So we always say, design your wall assemblies so you really want to keep, bulk moisture on the outside from ever getting in, but assume it's going to get in and make sure it can't dry out. One more quick thing on that. If I'm going to pick on John. Let's say John goes down to the river. He's wearing his clothes. This time you're wearing your clothes, John. And you jump into the river. What form of these four moisture things, which form of moisture transfer is making you get wet? Are you wicking water, or are you just getting basically immersed in water? So your bulk moisture. Okay, so John, why did you do that, John? Just for the name of science. Then he stands on the side there and just stands there like this. What mechanism is he drying by? That's an interesting one. It's really diffusion. It's in other words, the water is diffusing through your clothes and then evaporating. So it's a kind of a trick question. But I guess what I'm saying is that buildings get wet quickly generally by bulk moisture problems and sometimes wicking. Buildings dry by diffusion, which is a slow process, right? And the one thing we arguably, since we're in a mixed climate where it's some of the year there's more moisture outside than inside, but some of the year there's more moisture inside than outside. That would be the winter time when it's the other way around. So we just want to make sure our assemblies we haven't stopped them from being able to dry. Does that work? Okay. I didn't mean to beat this to the ground, but I think those are some important concepts. Nothing in the energy code is requiring you to put a vapor retarder anywhere. Nothing is preventing you from putting one where you think you need it. So that's always important to emphasize. The commercial building world is playing in the big leagues, and it says you need to be smart enough to figure it out. And if you need help, get a consultant. Okay, or I guess you could learn it all from listening to Burke's online modules. Does that make sense? Okay. All right. Let's wrap up building science. That kind of finishes that out.